Today we will talk about mixture model and the EM algorithm. So first, let me start reminding you the types of distributions that you have already seen in the class. What we will do today, we kind of combine two of them. So the first distribution, the first generative model that we've seen were multinomials. So in the case of multinomials, we assume that we have some set of possible outcomes. If we're talking about language, it will be maybe the vocabulary, capital W. And we would also assume that we have certain likelihood to generate particular word W in this vocabulary. So it means that the likelihood of generating certain W given parameter theta will be theta W. Another example that you can be thinking about is about a dice. Maybe our dice is a normal dice and it will be 1 divided by 6 for every single edge of the dice. So if it is some inappropriate dice, you would have different probability for different sides. And we know that the sum of all these parameters, because they form probability distribution, have to be 1 if we go over all the words in the vocabulary, and we also assume that each one of those thetas are non-negative number. So now we've said that given this multinomial, we can actually compute the likelihood of a certain document. And since we're generating all the words in the document independently of each other, we can just say that the likelihood of a document D, which contains a number of words from W1 to Wn, given thetas, would be just a product when we go through all the words in our vocabulary, and then we look how many times the word appear, and we would multiply theta W accordingly. So if this will be the count of the words W in the document D, then this expression will give us the likelihood of the document. Okay? So this is one example of a distribution that we've seen. And then we've seen a different distribution, which were called Gaussians. Gaussians. So in this particular case, it's very easy for us to think about Gaussians in terms of, kind of the geometric view. We assume that we have, all these different points, and these points would have a particular center, and they also would have variance. And this is the two parameters that will control our Gaussians. I will establish, where the points are kind of clustered together, and this is, we call it mu. This is the center of the Gaussian, and we will also have the variance for which we will use this notation sigma square. And now, depending on how do you decide about the variance, we can have all the points which are really closely kind of collocated together, or they may be farther spread around for large values of the variance. So in this particular instance, we can actually look at the likelihood of certain point to be generated by a given Gaussian. So given mu and given variance, again, we can look at one point, and let's say we have several different Gaussians, and it will have different probability depending on which of these Gaussians we selected, which mu and which sigma square we selected. And in this case, we will sometimes use slightly different notation, but the idea is exactly the same. And here we can just write it 2 square d2, and I remind you the d is just the size of our vector, correct? If here we are in 2D, but typically we are going to be looking at much higher dimensions, and then we will do exponent minus 1, 2. So here it's actually very easy to see that the points which are farther located from our center would have lower probabilities at points that are very closely located to the center. So, but what I want to tell you looking at this distribution, that what we've done in the previous lecture, we actually answered a number of questions, and we've seen that independently which generative model we looked at, we kind of ask similar questions and solve them using similar technique. So the first question that we ask is how I can actually estimate these parameters. How do I know what are those setters, zeta w's in the case of multinomial, or mu and sigma square in the case of Gaussian? And the criteria that we used was maximum likelihood estimator. So we estimated parameter using MLE, maximum likelihood estimator, and what we've said that given some particular document D, we are looking for the values of these parameters that are going to give the highest likelihood to our observed data. And if you remember, we took our usual tricks, we took derivative with respect to parameters, made them equal to 0, and demonstrated how these parameters would look like. And we did the same both for multinomials and for Gaussians. And not surprisingly, what we've got is very consistent with our intuition. For instance, in the case of Gaussians, we demonstrated that the estimated mu for our Gaussian will be just a mean of all the points. It's 1 divided by n, sum of all the points x, phi. And similarly, we also demonstrated using exactly the same technique that if we're estimating our sigma square, it's going to be 1 divided by n d, sum from 1 to n, xi minus mu squared. So this is the estimate that we are going to get if, again, we take the corresponding expression, take the derivative, and that's what you did in your exercises, and you will get this expression. We also demonstrated that once you set up these parameters, you can actually use these generative models for classification. You will estimate the model for the positive class, you will estimate the model for the negative class, and then you would assess, is it more likely that my point comes, has higher probability to belong to the positive class versus to the negative class. But today I want to move to the different class of distribution, which in some ways will be the combination of these two. And they're called mixture models. And mixture models are actually very useful for describing many real-life scenarios. But let me first demonstrate to you what are mixture models, thinking about them, again, from the geometric perspective. So what I drew you here when I was talking about Gaussians, I demonstrated to you the case when I have a single Gaussian, correct? So this is a single Gaussian. Now imagine to yourself, I am doing the following drawing. So in this case, you can still say, we have one Gaussian. This would be the centroid of this Gaussian, and this would be, with a very high variance. But we clearly see, looking at this example, that we actually have two clusters, not a single cluster. So, or if I may draw 4, 5, or 6, the more we draw, we can always say it's something like really one big Gaussian. But we can do much more refined modeling if our, generative model can actually explicitly allow us to talk about, the fact that we have several different clusters. And that's exactly where we are introducing these mixture models. When we are talking about mixture models, we would assume that we have several mixture components. Each one of them will be a Gaussian. So we will have, let's say, K is the size, this is the size of our mixture model. And then we would assume that each Gaussian would be represented by its own private mu, let's say mu j, and sigma square j, okay, where j goes from 1 to k. So now, in this particular case, we will have two components. where j would go from 1 to 2, and each one of them would have its own mean and its own variance, okay? So now it should be already reminding you our conversation about clustering, because in the case of clustering, you had several clusters, correct? And we describe each cluster maybe by representative of that cluster. But here we have the next level of refinement. First of all, we are not only reporting the mean of the cluster, we are actually looking at the variance, how spread is the cluster. We would also introduce another piece that we want to capture here, is how big is this cluster? How likely is that this cluster takes more and more points? That's why, in addition to having mixture components, we are also going to have mixture weights. And what mixture weights means that now each one of these guys would come with its own likelihood. And this will be a multinomial. The sum of these probabilities would go to 1. So this is a multinomial. And we can think about the process of generating a point with this mixture model as two-step process. The first step, you will kind of throw your dice and decide which one of mixture component is used to generate our point. So what we are going to do, we are going to first draw from our multinomial, when we are selecting a particular cluster, okay? Then, after I selected the cluster, it means that I selected already its mu of that cluster and sigma square of that cluster. So again, the process is, imagine to yourself, you first have a dice, you throw the dice, you find yourself a Gaussian, and then you draw from that Gaussian according to its own parameters. Okay? So this is the generation step. And another important distinction between this model and what we got when we were doing k-means clustering or any clustering, this is actually a soft clustering model. Because for every point that we have here, okay, let's say we have some mu and sigma square here and mu and sigma square here. Every single point here can be either generated by this guy or by that guy, just with different probabilities. So here we have a much more refined way to talk about our distribution, because every point kind of belongs to different components just with different likelihoods. So this is our mixture model. So let's just think what kind of parameters we have. So again, our parameter theta, like we define above, the parameter theta would contain all the mixture weights. You can represent it by this polynomial. Then they're going to have mu for each one of the components. And then we're going to have sigma square for each one of these Gaussians. This is our thetas, okay? So this is, you see, there's a whole family of these parameters that we need to determine. But before we're going to start having a conversation of how actually to compute these thetas, I just want to show you yet another piece. How can we compute the likelihood of a particular point to be generated given these parameters? And if you look here, I asked this question in the case of a single Gaussian, correct? When we have our parameters and we ask what is the likelihood of x. So here, remember that when I was writing x and theta, there is actually the whole family of these parameters. How can we do it? And now, you remember that the point may be generated from various different clusters. We don't know which one contributed to it. So what we will do, we will marginalize over cluster assignment. Meaning we would look at the likelihood of it being generated by all possible clusters, and then we will sum it up. So in this case, we are going to go from 1 to k, and then look at the sum up the likelihoods of the point being generated for each one of the clusters. So it's going to be pj and then n x, the likelihood of it generated by the mixture component j. So now we have everything we need, to think about a mixture model. And the next question for us is how we can actually find all these different parts, all these different parameters, given a specific assignment of points on the plane. And you can see that there is a lot of dependency here because, in general case, we don't really know from where all these points come. We don't know to which cluster it belongs, and that makes the matter much more complex. So let me first write you down the likelihood. We will do exactly the same thing as we've done before. We said, okay, I'm giving you some set of points, Sn, correct, that has n points with parameter theta. And what de facto it means that we need to go and multiply, because all these points are independent. We're going to go from point 1 to point n and multiply its likelihood to be generated by this Gaussian. So we can just write it sum from 1 to k, pj, n. So now I have this expression, and given this expression, I want to take the derivative of it with respect to my parameters, make it equal to 0, and find the parameters. It turns out it's actually a pretty complex task. So what we will do now, we will start with an easy case. The first case that I will consider with you is the case which is called observed. I would assume that somebody gave me these points, but they actually gave me the hard assignment. They say this point belongs to the first cluster, and this point belongs to the second cluster. You can imagine them, if we would have here red and blue, that some of them are red and some of them are blue, so we have no uncertainty. We know your belonging. And I would demonstrate to you how we can solve that piece. And if we understand it well, we can very easily translate it into the case where the assignment is not observed, and that's where we're going to be talking about EM algorithm. So right now, the next question we have to address is how we can find all the parameters that we're interested in, which would be the mixture weights, and then the mu's and the sigma square for each mixture component. And the easier case here is to start with an example where we know exactly where each point belongs. And we will call this case observed case. Now, what I am going to do in the observed case, I'm going to introduce some notation which would look some cumbersome, and you may be thinking, why wouldn't we use some simple notation? Why, we're making all these really complex formulas when it's so simple? And the reason we're going to be doing it, it's not because of my cruelty, but because we afterwards, using this notation, directly translate them to unobserved case, which is more complex. Not much more complex, but still. So let's start with the first piece of notation. So this piece of notation would tell us this is an indicator function which would be equal to 1 when we know that point xi is assigned to j, to our mixture component j, and 0 otherwise. Okay? Again, as I said earlier, this is an observed case. We have a hard assignment. So for every point I, there will be just one j to which it belongs. Okay? The next point that we are going to make is actually now to use this particular notation to rewrite this formula. Because remember, what we're trying to do is to find p mu, and sigma square. So what I will do now is to do what we've done before, to say that what expression I'm trying to maximize. So we will take this likelihood expression, and as we've done in the past, to do it log likelihood, okay? And I will write it using this notation, you would see. So let's start here. So we will go, okay, I am logging it, so the product is going to become a sum, okay? So I'm writing sum from 1 to n, okay? Then we go through all the points, and then we are looking to which clusters do they belong. So we're going to go through every cluster, like for every point we're going to see to which cluster it belongs. So I'm going j from 1 to k, okay? And then within that particular cluster, I'm only going to take points that are hard assigned to this cluster. So we're going to say delta j I log p j and x. Okay, and now I am going to change this summation. So in this summation, you see we go through all the points, and then for each point we go and find the relevant cluster and then sum up the expression. What I can do here is actually switch the two and make this computation, instead of going through the cycle through all the points and through the clusters, instead I am independently will do this computation for each individual cluster. So I am going to rewrite this expression, putting now the internal sum on the outside, j from 1 to k, and then we are going from 1 to n, and this whole expression. Okay, so let's just look at this expression. So what this expression actually demonstrates to us, that whenever we are trying to find the parameters that optimize, for each mixture component, we can actually do this computation for each cluster independently. We can independently find the best parameters that fit this cluster, because the fact that these points are observed, we actually know where the point is belonging to. So we can separately find here the mu and all the stuff, and we can separately do the computation here. So now I want you to look back at this specific expression. So we're kind of coming back to the situation that we already have been in. We're separately looking at each one of these Gaussians, and for each one of them we can do the computation similar to what we have done before. So let's see how it unrolls, okay? And I would like to, again, use here this notation that hopefully at this point already makes sense to you, and to compute different quantities. So let me start with the first quantities that I'm interested in. The first thing that I want to do is to compute how many members belong to each class using this delta notation, to each cluster. So we're going to say n, this is a number of estimated number of points that belong to cluster J. At this point, we just need to sum up over all delta ij when I goes from 1 to n. So we will see here for all the points that belong to cluster J, and only for those points this would be equal to 1, so we're going to sum and it will give us a number. So now, how can I compute my first parameter that I'm interested in? This will be this guy. how can I compute the mixture weight for cluster J? Very simple, using maximum likelihood estimate. We're just going to say, again, we can be really formal here and take the derivatives, make them equal to 0, and maybe we should keep it for the exercise. But if you go through it, what you will discover, as we've done before, something very intuitive, that it's just going to be the number of the members in this cluster divided by total number of points. So this will be the weight for the mixture component J. Now, similarly, we can compute the mean of that cluster. And here comes a component, two ways to think about it. One way to think about it, and again, some of you can just take this internal expression and differentiate it with respect to mu and find it and go through the whole process. And what you will discover that it will have a very similar shape as what we've done for individual Gaussians. We're just going to sum up all the points and divide by the size of the cluster. So we will, in this particular case, what we will get will be sum of all the points that belong to this cluster. And again, how do we say it? We go through all the points from 1 to n. Divided by the size of that cluster. So this would be our estimate, maximum likelihood estimate for the center of the component J. And the next thing that we need to do is to compute the variance. And again, we can go take the derivatives, but what you will get would be an equivalent of this formula that was developed for the case of a single Gaussian. So we are going to get 1 divided by the size of that component, D. And now we will go select all the points that belong to that mixture. So again, this is a mechanism. Our indicator functions just make sure that we're selecting points that really belong to this specific cluster. So what I've done so far, I've demonstrated to you how, given the observed case, when we know to which component each point belongs, I've demonstrated to you how we can estimate all the parameters that we need to define our mixture of Gaussian. So the next question that we need to answer is how can we do it if we actually don't have at all information about the identity of the points. Okay, so before I start describing to you how can we do it formally, I want to give you an intuition how it would go. So what did we do here? The reason we introduced this notation, this delta, it's actually a hard count. We know the point either belongs here or it doesn't belong. It was 0 and 1. Now, one of the powers of our mixture model, that actually model doesn't solely belong to this cluster, we know that it can be generated from different ones with different probabilities. So now, instead of talking about hard counts, belong or doesn't, we're actually talking about soft counts. How much does this point belongs to this particular cluster? But you know, when I just give you this spread of white points, I don't know how much does it belong to the cluster because I don't have the parameters. You agree with me that if I will actually specify to you all the parameters that we need to know, you know, all the mu's and zeta square and p, you can actually answer this question. You can say how much does it belong to this cluster versus to that cluster, but you don't have it. You don't know. It's kind of chicken and egg problem because you don't know where it belongs, but you also don't know the parameters. So what we are going to be doing here, we're actually going to break it down. And intuitively speaking, what we will do, we will say, okay, let's say I randomly guess the parameters. I randomly selected the p's, and I randomly selected the mu's, and I randomly selected the sigma squares for each one of those components. Okay. We can later discuss what does it mean randomly selected and what implications have, but for now just say you magically come up with some things which may not necessarily be the perfect one, but you come up. This is your first estimate. And in your head you should be thinking about k-means clustering. You remember when we started talking there, we just randomly selected the representative of each cluster, we randomly selected them. So here we're selecting randomly a bit more than that. We're not only selecting the mu's, but we're also selecting the sigmas, and we're also selecting the mixture weights. So I selected them. Now what happens? Now I can actually compute the soft counts. For each point I can say how likely that this point actually belongs to this cluster. This will be sort of a soft equivalent of this measure. Here I just say, is point I assigned to cluster J? Now I say how likely is that the point I comes from the cluster J. It's not going to be 0 and 1, it could be some other number. But what it actually means is that instead of using delta, I can use here the probability that the point is assigned. So as previously when I did all this computation, instead of taking this indicator function 0 and 1s, I'm just going to be using probability, and I will do exactly the same computations. So what would happen here, that after I made these guesses, I can kind of compute this soft assignment of points to clusters. And what will be the next natural step? Now the points belong to the clusters. I can actually go back and recompute the parameters. Again, maximizing my likelihood of observed data. And once I recomputed the parameters, hopefully in a better way, which maximizes the likelihood, I can now go and reassess the soft counts. And I can continue these two steps. So the first step is expectation. It's called expectation maximization. The first one, we're computing the likelihood that the point belongs to certain mixture component, and then we maximize the likelihood by reassessing the parameters. And we can continue doing these two steps until there is no change in our parameters, or they're close enough. So for now, just let's assume that we know how to do initialization, and I will talk about it later. And let's just focus on these two steps. So the first step, the expectation is step and M step. There are two steps that we are going to address. And in your head, you can think about k-means clustering, which would be very much a hard version of the same idea. Okay. So, and to make it more visual for you, I want you to look at this slide where you see the points after I kind of randomly guessed, these parameters. And now if you look at the points, you would see that the points are colored in multiple colors. You can see that we have like a red and the blue, and maybe some points are more belonging to the red cluster and some are more belonging to the blue cluster, and so on. And you can see that as we do re-estimation, the red and blue and other colors kind of move around, and then the coloring of each point, its kind of allegiance to different mixture components changes, and we continue going through these steps until we come to the convergence. So it's graphically very easy to see. But let me now go back to kind of formal description, and what I will try to do, I will try by first introducing you, introducing you some notation, which is very kind of expected notations. And then we will very much reuse this language to do one of the steps of the algorithms, okay? So again, the first step for us, again, we randomly, this is the 0 step, randomly initialize all the thetas, which in our case means all the mu's, all the mu's, all the thetas, and all the probabilities. Okay. This is random initialization. Next, the first steps that we are going to do is called E-step. This is a step that you go for each point and say exactly the same notation as you've done before. What is the likelihood that my point I belong to cluster J? Okay, and we will use posteriors to make this assessment. We are going to say it's going to be Pj n xi mu j divided and we can do further estimation. You remember we look how we can actually compute the likelihood of x being generated by our mixture. It's just gonna be sum of this expression along all the mixture components. I would not write it down, but you can quite imagine what we do. We take this over all possible j's from 1 to k and sum them up. So the point that I'm trying to make that after I give you these numbers, you can make this computation. Okay? So this is pretty straightforward. And this is a place, if you remember the pictures that I showed you, this is a place that would allow you to say how much red versus blue versus black the point has. Because the coloring at that point would be proportional to its likelihood to be of the red cluster. Now comes the next step. So great. Now you have all your points, and we know how much of red or blue or black color. And what I want to do, I want to re-estimate my parameters to make them more consistent with the current assignment of the soft counts. Okay? So this is a step when I want to recompute the Pj, the mu j, and the variance for cluster J. That's what I want to do. Okay, so how can we do it? So let's think how the computation changes when we, instead of using our deltas, we're going to be using probabilities because they reflect our soft counts. So let's start with the first point. How do we compute here nj, which is the size of the cluster? So here now when we're talking about the size of the cluster, we will just take the soft counts, how much the point belongs to this cluster, and sum them up. So how we get it? We go from 1 to n and look at probability of a point to belong to this cluster. The next things that we need to do, we need to compute the mixture weight of cluster J. So what we will do is exactly the same thing. We're going to take the size of the cluster, which in this case is computed with soft counts, and divided by the number of points. So we don't even need to change the formula. Okay, so let's look what happens here. Here, what we've said, you know, the same way we were inspired by what happened in the real Gaussians, we took the expression that we have that we had before, and just we said, in order to say that the point belonged to the cluster, we use this indicator function. Now, instead of the indicator function, it's not enough for me to say whether it belongs or it doesn't, because it belongs to everybody with different probabilities. I am just gonna weight the point in the sum according to its likelihood to belong to that cluster. So in this particular case, again, we can just rewrite this expression, mu j, we're going to say 1 divided by nj, I from 1 to n, p j I x I. And in a very similar fashion, you can do the same computation when we are computing the variance. Again, we're going to substitute here the delta with a probability. And once we completed the m step, the result of this m step, and I would not write you the estimated variance, but you can quite imagine how it looks like. Now I have all the parameters that I need after my first step of EM. Now I started with totally random numbers. I did the computation, and now I should have a better estimate of the parameters. So since I have now the new parameters, I can go back and recompute the probability of the points to belong to a certain cluster. And once I complete that, I can go back and forth. So we will continue this process until convergence. So now I want to emphasize that these numbers, how did they come about? How, for instance, this number came about? We can actually take, again, our expression for the likelihood. And because the points are now, we know to which cluster they belong, we can take the expression for the likelihood, take the derivative, do the whole computation, and demonstrate that they will have this specific form. You don't have to do it, and hopefully you are convinced based on our conversation, but if you want to, you can go and do the whole computation the way we've done it in all these other situations and demonstrate that this will be the form of these expressions. And again, this so that you may be thinking, so why I didn't take my original expression, which is here, just logged it, okay, and just did the derivation directly. And the reason we didn't do it, because whenever we are taking the log of this expression and we're getting sum of log of sum, and all these parameters are intertwined, it's actually really non-trivial for us to compute the estimates of this of all these variables, because they're very interconnected. So therefore, we are taking this way where we are breaking this dependence by first assuming what are the parameters and computing the likelihoods of points belonging to different clusters, and then use it to do the computation. And if you look now at the slide, you can really see how the M and E step interact, kind of bringing more homogeneous points together and coloring them into the same color. So now I want to say another two things related to the guarantees related to EM algorithm. What we can say about EM algorithm is that it's guaranteed to converge to converge locally. So, which means that if we are starting with different random starting points, we may get very different answer depending where we start. And this is actually one of the very weak point of the algorithm, is that you really need to know how to initialize, or you need to have some hunch how to initialize it to bring you to a good spot. And you can think, for instance, in our case of mixture model, what would be a reasonable initialization? So, for instance, what you can do here, you can just run k-means algorithm and get the muse from k-means algorithm, which will be your original muse, and then maybe use the global variance as a variance for each one of the clusters, so that every cluster has reach of all the points. And typically what people do in real problems, and EM is really widely used, sometimes people may kind of look at a more simplified version of the problem to utilize it as initialization to more complex one. And there are lots of interesting uses of EM, and I hope you will explore some of them in your exercises. Thank you.